So Dr. Weifeng is a fellow of Alibaba Cloud Intelligence and the chief scientist of heterogeneous computing at Alibaba Cloud Infrastructure. He is in charge of technologies ranging from AI accelerator benchmarking, AI compiler, performance co-optimization, and the unified scalable heterogeneous acceleration platform. So his talk today is hardware-software co-optimization for efficient privacy-preserving computing in AIoT devices. Okay, Dr. Weifeng, the virtual floor is yours.
Thanks, Wei, for the intro. Hello, everyone. This is Weifeng from Alibaba Cloud Infrastructure. Really happy to be here and discuss privacy-preserving computing with a great expert from both industry and academia. We know that privacy and performance will likely be the driving force for the adoption of machine learning on the edge and IoT devices going forward. For the on-device processing, we certainly guarantees privacy without transferring data over connected devices. However, it's not always possible for us to keep the data local. And because we know that only data is shared and exchanged, then its value can be maximized. So in this talk, I'm going to talk about how we maintain the data privacy while making AI computing more efficient. Here's the outline of my talk. And first we'll see why data privacy and protection is important in AI. And then we'll look at the main approaches for privacy protection. After that, we'll discuss how the general AI acceleration leverages heterogeneous computing for performance. And finally, we'll discuss how we can use a similar idea to speed up privacy-preserving computing. With artificial intelligence advancing to its maturity, more and more AI systems have been deployed in many scenarios of our daily life, like in the logistic facilities, in hospital, on the street, or at our homes. For example, like Siri and Alexa Home Assistant, they use AIs for speech recognition. And we also saw that city traffic management, they use like secure cameras to detect cars and pedestrians. At the hospital, doctors start to leverage in 3D segmentation for tumor diagnosis. So with all those IoT devices deployed, we see massive amount of data generated from these devices, like videos, voices, and images. Some of this data will be processed at the edge, but most of them will be transferred to cloud for further processing. So with frequent data acquisition and remote processing, people have raised a concern over the safety of AI system in several aspects. For example, like, is the system vulnerable to various attacks? Or is the system robust to small variations of your input data? Has the data been collected in an ethical manner? Or does the system protect your personal identity and much more? Privacy certainly is not new. In 1996, Health Insurance Portability and Accountability Act was created as a U.S. federal law to establish national standards to protect the patient health information. Recently, this data protection expanded beyond the patient health. So this goes to like a more general data. For example, recently, European Union have created the General Data Protection Regulation, which governs how the personal data may be processed and transferred. And similarly for California Consumer Privacy Act, which enhances the privacy rights and the consumer protection for residents in California. At latest, China's new personal information protection regulation, which just took effect like yesterday. And this law is going to control how data is going to be collected and processed. In the early stage of AI development, people are more focusing on AI functionality and the performance. But now with so many laws start enforcing data protection, and we have to look at more privacy, robustness, reliability, interpretability, and so on. And this set of AI properties it's going to be extended much beyond the traditional property we look at. And hopefully this set of property is going to make our AI more trustworthy and running on this mixing of trusted and untrusted computing hardware. So now let's look at the existing schemes for privacy preserving computing. We can simply categorize in this technology based upon their underlying techniques. For example, the first one is trusted computing. And we have a trusted executing environment, which uses a hardware-supported enclave for data isolation and protection. And also there's active development of trusted computing accelerators. The second category is cryptography, which for example, we have like a homomorphic encryption, which can provide end-to-end data protection without ever decrypting data before processing. Unfortunately, homomorphic encryption only supports a limited set of operations, which typically have linear properties. And another cryptography-based scheme is a multi-party computation. And they are also using the traditional cryptography to provide data protection. The next category is federated learning. And this is essentially a decentralized collaborative learning without really transferring data off your device. The last category I just put as a differential privacy and data masking. So we can see that all those privacy preserving schemes have a same goal. Essentially, they make the data available but invisible. So in this talk, I'm going to concentrate on how we address the issues in the trusted execution environment and the data masking, because we know that we cannot really enjoy a free lunch without paying a cost. So I'm going to look at how do we address this cost in these two categories due to a time limit. So what are the problems with TE? We know TE is a trusted execution environment where data is decrypted before execution, but stay encrypted whenever being outside of the environment. From this referenced paper of IEEE 2016, we can see that TE can be qualified with can be measured with like different qualities based upon these three criterions like functionality, security, and deployability. The functionality basically measures how the TE provide the physical protection of the data throughout its entire life cycle. And the security is a mechanism to avoid specific attacks on the system. And the last criterion is deployability, which essentially covers the performance, scalability of the system, and etc. Because TE usually has limited computing resource due to the isolation for the security purpose. So the computation inside TE won't really be able to enjoy the performance benefit of the system resource, even if they have powerful accelerators such as GPUs and NPUs. For example, we saw that like ARM trust zone-based TE is typically bound to a single core with limited parallelism. And also Intel SGX enclave may cause a performance slowdown as much as 20x. And in some observation, homomorphic encryption may suffer performance degradation up to like 3 orders of magnitude. And this performance overhead or the performance penalty really becomes a bottleneck of deployment of TE on the edge devices. So before we dive into how do we solve this problem, so then we look at in the general AI acceleration, how do we actually do in the performance speed up? This is an example from IMF comments regarding AI training performance. As we can see in the past few years, and AI training performance really gained almost like a 20x increase. And this goes much beyond the Moore's law, which only gave us like maybe a little over 2 times. And the push behind this, the faster growth is really the heterogeneous computing. And so now let's see, with this heterogeneous computing scheme, how does this work with the existing AI framework? Typically, heterogeneous computing accelerators, they have like a vendor-specific software stacks, and these are vertically integrated into existing ML framework. But this type of solution often has gotten some problems like fragmented solution with incompatible software stacks. And because of this, some of those, especially customers of those accelerators, may suffer like significant effort to adapt their software stack. And also tight coupling with a vendor-specific solution can also lead to a high maintenance cost. So at Alibaba Group, we developed one unified heterogeneous acceleration platform based upon like 2 innovations. The first one is a heterogeneity aware lowering and optimization, or short HALO. The other one is Open Deep Learning API, or in short, ODLA. So with this HALO ODLA heterogeneous acceleration scheme, and all these AI models can be compiled into C++ code with ODLA APIs. And then they can be executed on those domain-specific accelerators with ODLA compatible runtimes. The benefit of this scheme is that we only need to generate the code once and it can be executed anywhere. So we can quickly support our new accelerated architectures and deploy that to like various scenarios. And also the application can have a dynamic switching between these heterogeneous devices with a seamless migration. So with heterogeneous computing paradigm, we are able to enable multiple dimensions of parallelism, such as data parallelism, model parallelism, and pipeline parallelism, etc. And also the optimization techniques can be based upon performance-centric cost models. So with this cost model, we can do the model or task partitioning for parallelism, and also we can place different tasks on a computation device for acceleration. So this is for like a general acceleration of AI framework, but with a trusted computing. So how are we going to do this? So actually, if we really look at this, and we just notice that now instead of just dealing with the traditional performance and functionality, we are just basically handle additional dimension of the compute, which is the trustworthiness. So using a similar idea as a general computing, so we can expand our optimization techniques to do task partition for parallelism and the privacy protection, and do the device placement based upon the trusted or untrusted device. And similar idea basically also can solve this fragmented secure hardware problem, as we mentioned before. This privacy preserving computing, we are essentially changing this model partitioning heuristic from performance centric to privacy centric. So here, look at the how this privacy preserving scheme works. And here is the general flow. And for example, if we have this model with n layers, so we can use a privacy-aware model partitioner to divide this model into like 2 portions. And this can be done offline in a development environment. And in a deployed environment, and the first part of the model, which handles sensitive inputs, can be placed in a TE or trusted execution environment. And this will provide all the types of data privacy protection for you. And the second portion, which handles insensitive input, can be placed on a regular accelerated environment. So this way we'll get higher performance for the execution. So the basic idea for the privacy-aware model partitioning is we compute the similarities of feature maps with the original input for each layer. And then we find the layer where the similarity appears to reach a minimum. So how do we actually assess whether this intermediate feature maps is similar to the input or not? So there's a few techniques we can use. This including like KL-based divergence to gauge the similarity, or we can use a GAN-based discrimination between the feature maps and the original input. Here's a quick example to illustrate how the privacy-aware model partitioning works. As you can see, used from this right-hand graph, and after a few layers, the feature maps can be visually divided from the original image input. So that's probably the location where we should divide these models into the different portions. On the left-hand side, this basically shows the KL divergence range of each feature map. Clearly, you can see that after a few layers, they really reach the stable, more minimal state. It's the point where we can cut off this model to divide them. So another approach for the data privacy protection is data obfuscation. And the overall flow is relatively straightforward. On the left-hand side, you can see that, for the regular data input, so the raw imaging is going to be pre-processed and then just input to a model. So with the data obfuscation, so we basically are doing data masking after pre-processing. So now instead of just original the pre-processed input imaging, now we see the masked input. And this input itself, it's pretty much you won't be able to see the original features of your input. So with data obfuscation, we can clearly see there's some pros and cons. First, although with this data masking technique, and all those sensitive data stays within the local storage. And typically we choose more kind of a mathematically proven techniques to do the data masking. It's really hard to reverse or recover the original data. For the cons of this method, and because the model accuracy could be adversely affected, so retraining are typically required. But with this general flow, and we can apply several hardware-software co-optimizations to really reduce the computation flops. And one of them we're applying is like a model restructuring based upon how this model works on a specific architecture. We are doing like a full stack based optimization. And some of these data masking operations can also be strength reduced for more efficient computation. Often there's a case that we may also need to collaborative edge cloud-based training and inference paradigm. And the cases like we need to offload this computation because there's insufficient resource at the edge, or because there's a requirement for the data sharing, but we cannot really transport it directly to the cloud. So the overall flow of this paradigm is similar to previous model partitioning scheme. So we basically have models, and we divide into like two portions. And the first one is basically like a local network, so that we can do like a data masking. And then all those masked data will be we basically essentially desensitize all those data, and those data can be transferred over network to a cloud for training. And after the model is trained, we can do the cloud-based inference. And the flow is similar, so that the raw input is going to be desensitized and then transferred to the cloud for inferencing. So this is the unified platform we developed at Alibaba. We call the Senior Trust. And this essentially is a software co-optimization framework to accelerate the privacy-preserving computing based upon Outlier.Trust API. One thing I didn't mention was that Outlier is actually a configurable API. So we can easily expand this API based upon different feature sets. So for the trust, that's the new API we just developed, extended from our heterogeneous-based Outlier API set. With this platform, we can do a few things, including a TE-based optimization. I mentioned like a model partitioning. We are also doing like a scheduling and offloading. And for the data masking, we are doing a privacy-aware training and inferencing, and also data mask-based optimization. The privacy-aware partitioning scheme I already mentioned in the previous slide, like KL divergent-based or GAN-based. And our current platform is supporting a few hardware architectures, including Intel SGX TE and also ARM Trust Zone TE. Of course, like GPUs and CPUs or NPUs and some other specific domain-specific accelerators like ASICs, and also supported for the regular AI acceleration. And more support are also coming in our future development. This is the last slide of my talk, and I just want to show that we already open sourced our platform, and we call the Senior open source from Alibaba Cloud Infrastructure team. And I mentioned that we have this Halo optimization framework, heterogeneity aware Lorient optimization, and we also open sourced our first Outlier-based APIs. And because our Outlier.Trust API is still under development, and we are going to open source them soon. And this is the link of our GitHub, and we welcome communities to participate and join our effort with us to hopefully push this forward. And that's it. That's it, my talk. Thanks for listening.
Cool. Thank you, Dr. Weifeng. So if our audience has any questions, again, use the Q&A box to raise your question. It's wonderful that the tool is open sourced. And one question is, what kind of machine learning framework does Halo support?
Okay, Halo itself is can be used standalone or can work with the existing framework such as TensorFlow and PyTorch. We basically develop like a bridge APIs so that they can seamlessly plug into the existing framework. And the one we open sourced can support PyTorch and TensorFlow.
Thank you. Okay, if there are no further questions from our audience, we will move on to the next speaker. Thank you, Dr. Weifeng. I also want to extend our gratitude to all the tinyML strategic sponsors who made this event possible. At the executive sponsorship level, we have ARM, my old employer, who provides the software and the hardware foundation, tinyML. Edge Impulse is the tinyML platform for all developers. Qualcomm advances AI research to make efficient AI ubiquitous. Sentient offers end-to-end deep learning solutions for tinyML and Edge AI. At the Platinum sponsorship level, we have Reality AI adds advanced sensing to your product with Edge AI and tinyML. Renesas, who has big ideas for every space. With our golden sponsors, Latent AI develops adaptive AI for the intelligent edge. Maxim Integrated, who is now part of Analog Devices, enables edge intelligence. Seed Studio, they are the IoT hardware enabler. tinyML builds smart IoT sensor devices from data. SynSense builds sensing and inference hardware for ultra-low power devices. We will have some special partner sessions in the next few days, led by the sponsors we just introduced. At the silver sponsors level, we have Aeon Devices, Deep Light, AMSA Vision Sense, GreenWaves Technology, Gravity, HOTG, Imagine Mob, Kixel, Rexin, and SAP.